Sure, this is gonna not work. Okay, hopefully Kylie will join us very soon. Okay, so we are gonna start stoichiometry. I'm gonna start here and then I will move to the document camera. That way we can do problems and those people who are gone can figure out how to do them. Hopefully I can figure out how to work the document camera again. Okay, so stoichiometry, it is a process of using chemical equation to calculate the relative masses of reactants and products in a chemical reaction. That is a really fancy, actually, like book definition. Process of using a chemical equation to calculate the relative masses of reactants and products in a chemical reaction. So it's basically doing mole conversion problems to try and figure out how much of a reactant is needed or how much of a product is produced. So we are going to mathematically figure out how much of each reactant we need and how much each product should theoretically be produced. That is stoichiometry. It is using a chemical equation, it's using math, it's using moles to try and figure out, like, theoretically, how much do we need, and then how much theoretically can we actually produce. And of course, when we're doing something mathematically, it's really going to be almost perfect, but when we do it in a lab, when we actually do the reaction, a lot of times our theoretical amount does not add up to our actual amount because there's human errors. Okay, so stoichiometry, what is wrong with this? There we go. My computer is revolting against me. I'm just gonna put it all up there and then I'll just talk. That's not, okay, I'll go from here to here. So in Greek, stoichion means element. metry means to measure. So that's kind of where they get that. So we're going to be measuring elements. That's where that funky word comes from. It is based on what we call mole ratios, and I'll explain what mole ratios are once we get a chemical equation in front of us. So mole ratios are, like it says, it's the coefficients in a balanced chemical equation. It's how many moles of each substance is needed to do the chemical reaction, or how many moles of each substance is produced from the chemical reaction. And the mole ratios come from the coefficients in our chemical reaction. The stoichiometry, there's a lot of stoichiometry problems we could do. We could do mass to mole, we could do mole to mass, we could do mole to mole, we could do mass to mass. We're going to just go straight for the most difficult type, and we are just going to do mass to mass conversion problems. So we're going to start with a certain mass of a substance, and then we are going to calculate how much of a reactant is needed or how much of a product is going to be made. So given the mass of one substance, you're looking to find, and then, or given, and then we are going to calculate the mass of another substance. So basically, stoichiometry are mass-to-mass conversion problems. I do think it's easier just to jump right in and do the problems, but it's nice to have some steps to go back to. Okay, so how we are going to go about doing these problems, you always have to start with a balanced chemical equation. That is the first thing that you have to start with. All of you with earbuds in. You don't have music going, do you? Okay. So you have to start with a balanced chemical equation. That's the very beginning. If you don't have a balanced chemical equation, your mole ratios are going to be off. So the number of moles needed for the reaction and the number of moles produced for the reaction, if those mole ratios are off, then your results are not going to be correct. So we're going to determine which mole ratio to use, and we'll do all of this in a problem. So the first thing, balance the equation. The second thing, decide which mole ratios we're going to use. And basically, this is what we're going to be doing. We're going to convert the mass of substance A to moles of substance A. And then we're going to convert moles of substance A to moles of substance B. And then we're going to convert moles of substance B to mass of substance B. So it's a conversion problem. We're going to end up with 2 conversion factors in our problem. So mass A to moles A to moles B to mass B. And this is where that molar mass comes into play. We're going to use that again. At the end of our stoichiometry problems, our end result is called the theoretical yield, because this is theoretically what should be produced, okay, if everything went perfect in the lab. Like I said, the actual yield, what is actually produced when we do the chemical equation in the lab, is quite often not exactly the same as the theoretical, because you have human error. You've got measuring errors, your balance might not be perfect, you might lose a little substance in the weigh boat. But when we do a stoichiometry problem, we are calculating the theoretical yield. Like theoretically, what should be produced? Or theoretically, how much do we need? I'm waiting for my recording to stop. That, see if I can. There we go. Okay. Okay, so you need a calculator. If you do not have a calculator, let's do a few practice problems, and then all of that stuff that you wrote down is going to make a lot more sense. Do I have what? Okay, so the first thing I want you guys to do is write down this chemical equation, and then I'll walk you through how we do these stoichiometry problems. So C3H8 plus O2 yields carbon dioxide and water. That is our chemical equation. It is what kind of a reaction? Combustion. I like it. Yeah. I like it. Okay, so this says, and you don't have to write the example out. I mean, we'll walk it through. It says, calculate the mass of oxygen required to react exactly with 189.67 grams of propane. C3H8 in the reaction, that's propane, described by the following chemical equation. So it says calculate the mass of oxygen. So I like to put a question mark above what I am solving for. So it says calculate the mass of oxygen. So I'm going to put G for grams so I know that I'm looking to solve for grams. That's just for me to keep things straight. So it says calculate the mass of oxygen required to react exactly with 189.67 grams of propane. I like to just indicate what I have and where I'm going to. So I am given propane, I'm given the mass of propane, and I'm going to convert it to the mass of oxygen so I can see how much oxygen I need for this reaction to take place. Okay? So before we do anything, we have to balance the sucker. Okay? So let's start with that. You probably should use a pencil. This may or may not work. We'll see. So 4 and 6 is 10, and that gives me 5. I think that looks correct. Are we good? Okay. So the coefficients, I'm going to put a 1 right here. We don't normally, but just so you guys know, these coefficients are called mole ratios. So I would need 1 mole of propane to react with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of hydrogen. That's one way to read it. Okay, that's why we call the coefficients mole ratios. You could also read it like this. You need 1 molecule of propane to react with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of or 4 molecules of water. You can read it either way. Either way is correct, okay? But for stoichiometry, we like to look at these as, they are mole ratios instead of molecules, okay? Because we have to go from grams to moles and then moles to grams again. So we're going to call them mole ratios. So the thing I'm going to do is I'm going to start with what I'm given. 189.67 grams of C3H8. Can you guys see that? Are we okay? Okay. So that's what I'm going to start with. So I need to eventually convert it to oxygen. Now, the first thing I have to do is I have to convert propane, my mass of propane, into moles of propane. So I'm going to use the molar mass. 1 mole over grams. I have to calculate the molar mass of C3H8. So I'm just going to do it over here off to the side. Where do I have room? I have carbon. I have 3 carbon at 12.01. It's barely on the page. I have hydrogen. I have 8 hydrogen at 1.01 to give me 8.08. And 3 times 12.01 is going to give me 36.03. So I'm going to add those two together. There we go. To get my molar mass of propane. So 36.03 plus 8.08 will give me 44.11 grams per mole. So I'm just going to split that answer up, the grams per mole, into a conversion factor. So 1 mole of propane is going to have a mass of 44.11 grams. That's where my molar mass goes. And I am going to label my substances because I am switching from propane to oxygen, so it's easier to keep things straight. So now my grams of propane are going to cancel out. And I'm sitting at moles of propane right now. Okay? So I need to convert moles of propane into moles of oxygen. So this is where I'm going to use my mole ratio. Since I have propane here, I need propane down here. So I'm going to use my coefficient. 1 mole of C3H8 is the same as 5 moles of oxygen. So I'm going to do 5 moles. I'm just using my coefficients of O2. So I switch substances using my coefficients, which are mole ratios. Okay? So it's a 1 to 5 ratio. So it's a 1 to 3 ratio. It's a 5 to 3 ratio. It's a 5 to 4 ratio, or it's a 3 to 4 ratio. We are using the 1 to 5 ratio, or I should say the 5 to 1 ratio, since those are the substances we're dealing with. So now my moles of propane are gone. So I have totally gotten rid of propane, and now I'm sitting at oxygen. So I'm going to go one step further, and I need the molar mass of O2. 32.00 grams of O2 is the same as 1 mole of O2. So now I'm getting off the page here. Let me take that back just a little bit. I don't like that. There we go, that's a little better. Okay, so now it's math. Now it's all math. So I'm going to multiply everything I have on the top straight across and divide by anything that I have on the bottom. I started with 5 sig figs, so I'm going to end with that. So 198.67 times 5 times 32 divided by 44.11. So 600, and somebody verify my math, 0.99. Oh, I did?
I got 688.
Oh, gotcha. You got 688? Okay. Thank you, guys. 187.67. 5 times 32 divided by 688. 688.14 grams of oxygen. So
14, because I got 688.025.
So, okay. How did I get 688? So I multiplied. Maybe you did what I did, because I flipped 189. I think I flipped those two. So 189.67 times 5 times 32 divided by 44.11. Oh no, maybe I was right. Did you get 687.99?
Yeah.
Okay. You're throwing me under the bus.
I wrote the propane thing wrong.
Okay, you're cool. So 687.99. There we go. So does that make, okay, are we good? So in order for this reaction to occur, if I start with 189.67 grams of propane, I have to have 687.99 grams of oxygen for this reaction to happen. Okay, so that's what we're doing. We are trying to figure out how much of a reactant we need or how much of a product is made. Okay, those are the two things we're going to be looking at. Now, this is the theoretical yield, and I'm sure I spelled that wrong, but this is our theoretical yield. Every time you do a stoichiometry problem, your answer is your theoretical yield. Okay, it more so pertains to your product, but this is like theoretically, if everything was perfect in the reaction and there was no spillages or anything, that's exactly how much we would need for the reaction to happen. Okay, so let's do another one. Oh, look at that. All on one side. So ammonia is used in huge quantities as a fertilizer, as you know. It is manufactured by combining nitrogen and hydrogen according to the following equation. Calculate the mass of ammonia that can be made from 2.63 grams of hydrogen. So what's the first thing we have to do? Balance. Got to balance it first. So let's see. We go 2 here, and we go 3 here, and we're good. Okay, so calculate the mass of ammonia. So I'm going to put my question mark right here. And I'm going to put my mass up here just so I know what I have and I know where I'm going. So I'm given hydrogen and I need to figure out how much ammonia I'm going to produce in this reaction. So I'm going to start 2.63 grams of hydrogen. Let's go up here. Of H2. The first thing I'm going to do is I'm going to convert mass to moles. So I'm going to put my 1 mole of hydrogen on the top, and the molar mass of hydrogen is 2.02. You guys with me? Each hydrogen is 1.01. I can't do much math in my head, but that one I could do. So this is H2. So grams of hydrogen are gone, and I'm sitting at moles of hydrogen. So now I'm going to come up here, and I'm going to use my mole ratios. I'm going to use my coefficients. The mole ratios I need to use is hydrogen to ammonia. We don't care about this guy. It doesn't ask anything about nitrogen. So our 3 moles of H2 go on the bottom. So it's a 3 to 2 ratio. So my 2 moles of NH3 go on the top. Uh-oh, I don't know why I put H2O, that's my bad. There we go. So my moles of hydrogen are gone, and now I'm sitting at moles of ammonia. So now I'm going to jump on the molar mass highway. I'm going to say 1 mole of NH3 is equal to its mass in grams. So I actually have to calculate the molar mass of nitrogen. So nitrogen is 14.01, hydrogen 3 at 1.01, 3.03. So is that 17.04 grams of NH3. And now I'm going to put in my calculator. I'm going to do 2.63 times 2 times 17.04. And then I'm going to do divide. And I'm going to put 2.02 times 3 in parentheses on the bottom. And that should do the trick. How many sig figs am I starting with? 3. So I want to end with 3. 3 times 2 times 17.04 divided by 2.02. So you get 14.79? So we will produce 14.79 grams of ammonia. Oh, yeah, you're right. My bad. Sorry. 14.8 grams. Thank you. Hey, at least we don't have to use Avogadro's number, right? That's promising. Let's do one more. Yeah. Let's do one more, and then I will give you time to work away. Very bright. Work away on your assignment. So how many grams of magnesium oxide are produced when 10 grams of magnesium burn in an excess of oxygen in the equation below? It's like there's a glare. Okay, so first step is to balance. You guys just did this in the lab. So we're going to put a 2 here and a 2 here. And I think that should do the trick. So it says how many grams of magnesium oxide are produced. I'm going to put my question mark below here because I don't have enough room. And I am starting with 10 grams of magnesium. Gosh, we should do this in the lab and compare the theoretical yield to your actual yield. We might have to do that. Okay, so I'm going to start with what I'm given, 10.00 grams of magnesium. So I'm going from magnesium to magnesium oxide. So 10 grams of magnesium, I am going to convert grams to moles. So magnesium, I think, is 24.01 grams. And that is equal to 1 mole of magnesium. Magnesium?
24.31.
Oh, it is?
Yeah.
0.31? Okay, I trust you. My bad. I trust you. It's Friday at the end of the year, my brain. Yeah, you're good. Actually, it's 3-0. It's actually 3-0. Right? So you look to the right of it. If it's nothing, then you look to the number before the 5, and if it's even, it stays even. Yes. Okay, so grams of magnesium gone. I'm sitting at moles of magnesium. I'm going to go to my mole ratio over here. I have a 2-to-2 ratio. So 2 moles of magnesium over 2 moles of magnesium oxide. This is kind of easy because that basically cancels each other out. So then I have to go from moles of magnesium oxide to grams. So I do have to calculate there. So magnesium is 24.30, oxygen is 16. Let's make sure I did that right. Plus 16, 40.30. I think I might go home and balance my checkbook. Okay. We have 4 sig figs to begin, so we're going to end with 4 sig figs. When my mole ratio equals 1, do I even really have to put that in my calculator? Right? These two cancel each other out, don't they? So when you have that, you really don't even have to put it in your calculator.
Oh.
Ooh. You guys get 16.58? 16.58 grams of magnesium oxide will be produced. See, it's not that bad. They do. Yep. So exactly, back in August. Okay, that's stoichiometry. That's at least a starting point. There is more. We will add some more onto this. We'll do percent yield. We'll do limiting reactants, but this is the basics behind it all. Okay. Okay. So I am going to give you the rest of the time. Oh, work away on that assignment. I will hurry and total up your exam so I can get them back to you guys. Okay.